Hello everyone! Today we're going to do some integrals. Now just like when you learn derivatives, they don't teach you how to compute an integral right from the start. They kind of take you through different stages of how to compute an integral, which is what I'm going to show you. I'm going to give you the overview of all the different ways that they first show you. So the first thing to realize is that the integral is the area between a curve and the x-axis. So like here, all of this area between my curve and the x-axis, that's what the integral is actually telling you. So the first way that they show you how to do that is with Riemann sums. Now that's the thing you learned when you draw rectangles. Like for example, if I draw in some rectangles like this, and like that, and then finally at the end you would be finding the area contained within each rectangle. That's a Riemann sum, and it gives you a rough estimate of the integral, because you can see the area in the rectangles is not exactly the same as the area under this curve, because here's the area under the curve. So the area in the rectangles is a little bit more in this example. But that's the first way that they teach you, is with Riemann sums. So we won't do an example of that, but the second way that they dive into is with geometric shapes. Now, what you would do with this when you're first presented with this integral, now I'm sure you have easier ways to do this, but when you're first given this, you would draw a graph of y equals 2x plus 1 onto your coordinate plane. So that's a linear equation with a y-intercept of 1 and a slope of 2. So up 2 over 1, up 2 over 1, oops, and then finally up 2 over 1. So we get this straight line. Then, if you keep in mind that we're computing the area under the curve, or in this case it's a straight line, then we're finding the area in here, like this. Now if you look at that shape, it's sideways, but it's a trapezoid. So the area of a trapezoid is 1/2 times the height times base 1 plus base 2. So for this, it's going to be 1/2. The height of this trapezoid is going from here to here because it's sideways. So it's 1/2 times 3. And then base 1 is right here. So it's 1 unit tall. And base 2 is this other part from here to here. That ended up being 1, 2, 3, 4, 5, 6, 7 units tall. So this is what we get. So let's see. This is 8 times 3 is 24, and half of that is 12. So the answer to this integral is 12. All right, so now let's do the next one. Now this next one is the real reason why knowing geometric shapes is valuable, because we really wouldn't have any other way to do this function, the integral of it. So the square root of 9 minus x squared, you do need to recognize that that is the equation of a circle with a radius of 3. So what I would have is a circle centered at the origin with a radius of 3. The reason it's a circle is because it's coming from this equation. X squared plus y squared equals 9. And then if you isolate the y, you do end up getting y equals the square root of 9 minus x squared. So that's where it came from, and that's how we know that it's the equation of a circle. Now it's only the positive half, because they didn't write, see, they didn't say plus or minus, it's just plus. So it's just the top half of the circle. So it's really a semicircle. And this is not a coincidence, but the numbers that it's going from is -3 to +3. Those are the numbers on the x-axis. So from -3 to 3. So we literally just have to find the area of half of a circle that has a radius of 3. So we know that area of a circle is pi r squared. So we're going to do pi r squared divided by 2 because it's half of a circle. So that's going to be pi times 3 squared over 2. So it just ends up being 9 pi over 2. And we can just leave our answer just like that. Now, if you think about these geometric shape examples, this problem up here, this one, we really wouldn't have to do it with geometric shapes now that you've probably learned other ways to do integrals. But this one right here, if you think about it, there actually is no other way to do that integral other than just knowing that it's a semicircle and it goes from -3 to 3, so use the area formula. Really, the only other geometric shape examples that would really come in handy would be like an absolute value. Like if you had the absolute value of x that you had to integrate, you know that that's a V shape, and so you could draw the V, and then you could find the area under the V between any two numbers that they give you. Like if it's from -1 to 1, then it would be like from there to there. So you'd compute the area of those two little triangles. That's another handy one to know because there really is no other computational way to do an absolute value integral. Okay, so now moving on, there's also common problems in the calculus books that are like number 3, which is where they give you what I would call a parent integral. So they tell you the answer to a certain integral. Like in this example, I've told you the answer to the integral of x cubed from 0 to 1 is 1/4. So we can use that knowledge to figure out these other answers. So in part A, we're going to do all of this with graphing. So if you think of the parent function y equals x cubed, you know that it looks like this. And then they're saying from 0 through 1. So what they're saying basically is that the area in that little shape right here is 1/4. It looks like a triangle, but it's not really, because this edge of it right here is curvy. So the area right in there is exactly 1/4. So in part A, if you draw what this shape is, it's x minus 1 cubed, so we know that that's a shift to the right of 1. So the graph is going to look like this. What was happening at 0 is now happening at 1 instead. So there's a point there. And then this point right here on the parent function was 1, 1. So that's going to get shifted over to 2, 1. Right there. So now the curve is going to look like this. So it just really shifted to the right 1 unit. But ironically, it's asking you to integrate from 1 until 2, which is right there and there. So if you look at that, that's exactly the same little slice of the cubic. So that area is the same as before. It's just 1/4. So that's the same answer as the first problem. Now we have this other one, part B here. Let's move this over just a little. This is the absolute value of x cubed. So if I graph what that looks like, that's just when you take the original function and anything that was below the x-axis is going to get reflected above the x-axis. So this part will look the same as before. It'll pass through 1, 1 and the origin. But this part that used to be down here, that's going to get flipped up to here instead. So now we have this picture, and I'm going to ask you for the answer from -1 to +1. So -1 to +1 is the area under these two little chunks. So this right here and this right here. And those are actually identical to each other. This we know from before is a fourth. And this, even though it's on the other side, it's the same exact thing. You can just tell from the shape of it. It's also 1/4. So when you just add those together, 1/4 plus a fourth, that gives you the final answer of 1/2. Okay, so part A, you would have other ways to figure out part A other than using the parent integral, but part B, doing it with the absolute value around it, that's really handy to know how to use that parent integral to draw a new graph and then calculate the new answer to the current integral that you're working on. Now that brings us to the normal way, if you want to call it, of taking integrals, which is by knowing how to do antiderivatives. I'm going to show you one little preliminary thing by these stars. If you have a radical, take a second to rewrite it as an exponent, like that, x to the 1/2. Or if you have an x on the bottom, like let's say 1 over x squared, take 1 second to rewrite it first as x to the -2. That'll make your integrals much easier to work on. So in number 4a, I have one of those two things happening. I'm going to rewrite this as x to the -4 dx. Now this is just undoing the derivative. So we do the opposite of what we did when we did derivatives. We're basically going to take your function, you're going to add 1 to the power, and you're going to divide by that new power. So -4 plus 1 is -3. So I'm going to divide by that new power. So the final answer is going to be x to the -3rd over -3. And for right now, before you learn how to do definite integrals, just add c to that. Because there could have been any constant, like 10, 100, but if we did the derivative of any constant, it would just go away and be 0, so it would not have been showing up in that. Okay, so now the next problem, part B, the antiderivative of secant squared. If you think through the trig functions, the derivative of tangent is secant squared. So since we're working backwards when we do integrals, this answer is just literally tangent of x, and then you do plus c to that. Because if you think forwards now, the derivative of tangent is secant squared. And that's what is written right here. Okay, and then this final example, there's no way to just write down the answer to this. What we have to do is actually square it first. So if we do x cubed plus 1 times x cubed plus 1, that's our first step. So that's going to become, if we FOIL, x to the 6th plus 2x cubed, I'm kind of combining steps here, plus 1. So that's FOILed out. Now if we take the integral of that, it's doing the thing with the power to each term. So I add 1 to the 6, which makes it a 7, and then I divide by 7. Then I add 1 to the 3, which makes it a 4, and then I divide by 4. And then with the constant, that was the same as having x to the 0. So same thing, I add 1, which makes it a 1, and then you could divide by 1. So here's our final answer to this. It's just x to the 7th over 7 plus x to the 4th over 2 plus x, and then, don't forget, plus c. And that's our final answer. And so this is kind of the first stages of learning how to take integrals. The final thing being just to take an antiderivative. And then the next time I do integrals in a video, I'll show you u-substitution, which is the next level of difficulty with integrals. I hope that helps.